Welcome to the deep dive, and thanks for tuning in. You know how it feels, right? Trying to keep up with the really big questions, the exciting stuff happening out there, but it can be overwhelming.
Information overload, definitely.
Exactly. So that's what we try to do here, cut through some of that noise.
And today, yeah, we've got something pretty compelling, something that's definitely got scientists talking, maybe buzzing is the word.
A cautious buzz.
Ha, yes, exactly, a cautious buzz.
Definitely.
We're looking at some, well, very interesting, but still early stage observations, hints, maybe, of something huge. Life beyond Earth.
Right, and that's the key thing here. We're moving beyond just wondering what if and looking at actual initial data from a planet way out there.
Mm-hmm.
And our goal today really is to unpack why these first findings are generating excitement, but also, crucially, why everyone's being so careful, so methodical.
Absolutely. It's so important to understand right from the start. These are first steps, preliminary findings. Nobody, and I mean nobody, is shouting, "We found life." Not yet.
We're focusing on the evidence we have now and the careful scientific process that's unfolding step by step.
Okay, so let's dive in. Picture this. A planet. Way bigger than Earth. A super Earth.
Mm-hmm.
Now imagine it might be covered, like, completely in a giant ocean. Global scale. And on top of that, a thick atmosphere. Mostly hydrogen.
We call these Hyson worlds. It's a theoretical type of planet.
And even before this latest news, these Hyson planets were already really interesting targets for scientists, weren't they?
Oh, absolutely. I mean, think about it, a water world with a hydrogen atmosphere that's completely different from Earth.
Totally alien.
It represents a whole new potential kind of habitable environment, you know. It forces us to think outside the box of just rocky worlds like ours, expands the possibilities for where life could even get started.
And now, well, we've got the tools, don't we? Like the James Webb Space Telescope?
JWST, yeah.
Incredible instrument.
It's taken a first real peek into the atmosphere of one of these Hyson worlds. And, well, it spotted something.
It did. The data shows the presence of certain molecules in that atmosphere. And the ones causing all this careful buzz are dimethyl sulfide,
DMS.
DMS,
Okay.
and possibly dimethyl disulfide, DMDS. They're related chemicals.
Right, DMS and DMDS. Now, probably not household names for most people. So why? Why are these molecules the ones making scientists lean in a bit closer?
Okay, so this is the core of it. Here on Earth, DMS, it's basically made by life, overwhelmingly.
Like almost entirely.
Almost entirely. Primarily tiny marine life, phytoplankton in the oceans. They pump out huge amounts of it. It's part of the Earth's whole sulfur cycle.
Wow. Okay.
And DMDS, the other one, it's chemically similar. It's also been flagged, theoretically, as something that could be a biosignature, a sign of biological processes.
So finding them out there, it's like finding a potential fingerprint left by life.
Potentially. That's the key word. It's why it's intriguing. But as we keep saying, scientists are pumping the brakes hard on any definitive claims.
So what is the feeling then? Cautious excitement, intrigue.
I'd say cautious optimism is a good way to put it, or maybe focused curiosity. The detection is definitely interesting enough to warrant a lot more investigation.
Mm-hmm.
They're treating these molecules as possible biosignatures, indicators, not proof. The job now is to see if biology really is the best explanation or if something else could be going on.
Right. It's a clue, not a conclusion. And there's a statistical side to this too, isn't there? How sure they even detected these things at all?
Yeah, good point. The initial analysis puts the detection of DMS, or maybe DMDS, or both, at about a 99.7% confidence level.
Which sounds really high to me, a layman. Like 99.7%.
It does sound high, but in the world of astronomical detections, especially for something this significant, it's actually, well, it's not slam dunk territory yet. It means there's still a roughly 1 in 300 or 1 in 400 chance that the signal they saw isn't actually the molecule, but just random noise in the data, a statistical fluctuation, a blip.
Ah, okay. So still a small chance. It's just nothing.
A small but non-negligible chance, yeah. You need to be aware of that.
Got it. And what about the amount of this stuff? Did the levels they think they found match what we might expect?
Well, that's another really fascinating part. The estimated amounts are surprisingly high.
How?
Like potentially thousands of times higher than the typical background levels we find in Earth's atmosphere.
Thousands. Seriously?
Yeah, we're talking maybe 10 parts per million or more over there, whereas on Earth it's usually way down in the parts per billion range.
Whoa.
And that's significant because based on our current understanding of planetary chemistry, making that much DMS or DMDS without some kind of biological factory constantly churning it out, Well, it's hard to explain.
That really does make you think, doesn't it? Thousands of times higher.
Yeah.
But, okay, science means looking for all the answers. Are there non-life ways this could happen? Abiotic processes.
Absolutely crucial question. And yes, researchers are definitely exploring alternatives
Well,
vigorously.
like what? What kind of alternatives?
Well, one idea involves the planet itself. Maybe under that ocean, there isn't solid rock like here, but a huge ocean of molten magma.
A magma ocean.
And perhaps some weird geological or chemical reactions happening in that extreme environment could potentially produce these sulfur compounds. It's speculative, but needs looking into. And we also know DMS has been detected, for instance, in comets, which suggests there are ways to make it without life, at least in some cosmic environments.
Right. So just because it's linked to life here doesn't automatically mean it's life there on a totally different kind of world.
Exactly. The context is everything. We can't just copy-paste Earth biology onto a Hyson planet.
Which brings us back to that careful process. So what's next for the scientists working on this? Where do they go from here?
More data, basically. The immediate plan is to use JWST again, to re-observe the planet multiple times.
To see if the signal shows up consistently.
Precisely. To confirm it's robust, that it wasn't just a one-off weird reading, and doing that also helps improve the statistical confidence, to try and push past that 99.7% level towards something much more solid.
Makes sense. Build a stronger case. Is it just about telescope time, or is there other work involved, lab stuff?
Oh yeah, lots of work on the ground too. More theoretical modeling, trying to figure out if those abiotic processes like the magma ocean idea could really produce enough DMS-DMDS to match the observations. And lab experiments too, trying to actually recreate Hyson atmospheric conditions or magma ocean interface conditions here on Earth to see what chemistry happens. Can we make DMS without life under those specific conditions?
Right, trying to rule out the alternatives. You mentioned the confidence level earlier, the 99.7%, and how it's not quite a discovery level yet in astronomy. Could you elaborate a bit why the higher bar?
Sure. So that 99.7% corresponds roughly to what physicists call a 3 sigma result. 3 standard deviations.
Okay.
And while 3 sigma is often considered evidence in some fields, for major discoveries in physics and astronomy, especially something paradigm shifting like finding life, the community generally demands a much higher level of certainty, typically 5 sigma.
5 sigma. And what does that mean in terms of odds?
5 sigma means the chance of the result being just a random statistical fluke is incredibly tiny, like less than 1 in 3.5 million.
Wow, okay. A big difference from 1 in a few hundred.
Huge difference. So the current detection, while very interesting, is statistically much weaker than that 5 sigma gold standard. The odds against it being noise are maybe more like, I don't know, 5 to 1, maybe less, especially for the combined signal.
Yeah.
Individually, the stats for just DMS or just DMDS might be even less certain.
So, promising hint, but definitely needs that follow-up work to get anywhere near confirmed.
Exactly. Think of it like seeing a blurry shape in the fog. Could it be what you think it is? Maybe. But you need the fog to clear before you can be sure.
Good analogy. And it's worth mentioning, isn't it, that this specific planet, K218b, and this research group, there's been some prior discussion, some back and forth in the community already.
That's true, yes. This group has published previous results on this planet's atmosphere suggesting other interesting things, and those findings have sparked debate and scrutiny within the scientific community.
Which is normal, right? That's how science progresses.
It absolutely is.
Yeah.
Scrutiny, independent verification, debate, that's the process. And it just underscores why these new DMS-DMDS findings, while exciting, need that independent checking and critical evaluation by other teams.
It really shows science in action. So, okay, zooming out a bit, even with all these caveats, what does this finding, this potential detection, tell us about our overall quest, our ability to actually find these signs?
I think it's actually a landmark moment in a way. Regardless of whether this specific detection holds up in the long run, it demonstrates that our current technology, specifically JWST, has reached the sensitivity needed to potentially detect these kinds of biosignature gases in the atmospheres of planets orbiting other stars, even potentially habitable ones.
We could actually do it now.
We can do it. Observational astrobiology is becoming a real field, not just theory. We're moving from could we find it to let's go look, and maybe we just did. That's a huge step.
It really feels like we've unlocked a new level in the search. And looking further ahead, are there even bigger, better tools coming down the line?
Oh, yes. NASA and other agencies are already planning the next generation of great space observatories. Things like the proposed Habitable Worlds Observatory.
Habitable Worlds Observatory, okay.
It's being designed specifically with the goal of finding and characterizing potentially habitable exoplanets around nearby stars and searching their atmospheres for biosignatures. Much more powerful than even Webb for that specific task. So the capabilities will only improve.
So the search is definitely going to continue and get more powerful. Okay, let's try and wrap this up. What's the main takeaway message folks should have after this deep dive?
I think the key thing is this detection of DMS and potentially DMDS on K2-18b is arguably the most promising hint we've had so far of possible biological activity on an exoplanet. It's genuinely exciting.
Yeah.
But it is absolutely not confirmed. It's preliminary. It needs much more work.
Right. Don't rewrite the textbooks just yet. It's a stay tuned situation.
Exactly. More observations are crucial to confirm the signal is real and persistent. And more theoretical and lab work is needed to rigorously check if non-biological processes could maybe explain it.
Lots more science to come.
Lots more. The community will be digging into this intensely.
Still, even as just a hint, it really does give you a sense of the incredible possibilities out there, doesn't it? Makes you wonder what else JWST and future telescopes might find.
It really does, and it shows how fast our understanding of these alien atmospheres is evolving. This whole idea of a living universe, maybe it's not quite so far-fetched. Maybe it's starting to come within reach of our instruments.
A fascinating thought to end on. Definitely keep an eye on this story, folks. As the expert says, it feels like this is just the beginning.